What if an interstellar object whirling through our solar system is actually a nuclear-powered spacecraft sent by aliens to test how humans respond?
The discovery of 3I ATLAS on July 1st, 2025, instantly etched itself into the short but growing history of interstellar astronomy. This is the third confirmed visitor from beyond our solar system after one ʻOumuamua in 2017 and two Borisov in 2019. But that's not all. A prominent Harvard scientist is warning that 3IATLAS is emitting alloys unknown to Earth. In other words, he is hinting at the possibility of it being an engineered artifact. So, what do we know so far? Let's get started. 3. I-Atlas. What we know so far. On July 1st, 2025, 3I-Atlas became only the third confirmed interstellar object detected within our solar system. Its identification was made by the Asteroid Terrestrial Impact Last Alert System, or ATLAS, survey based in Hawaii, which has been operational since 2017, with the primary purpose of scanning the skies for hazardous to near-Earth objects. Unlike the countless asteroids and comets that orbit the Sun on closed, elliptical paths, 3I-Atlas was quickly recognized as an interstellar visitor due to the nature of its orbit. The trajectory was determined to be hyperbolic, with an eccentricity greater than 1, which means that it is not bound by the Sun's gravity and will eventually leave the solar system entirely. After its detection, astronomers quickly began calculating its orbital path, which confirmed that the object had originated outside of our planetary system. Its closest approach to Earth was projected to occur in late summer 2025, at a distance safely beyond the orbit of the Moon, but still within a range allowing for significant ground-based and space-based observation. After passing Earth, 3IATLAS would move outward. Crossing the orbital distances of the outer planets, the object will be ejected into interstellar space. As with the two previous interstellar objects, 1I ʻOumuamua, discovered in October 2017 by Pan-STARRS 1, and 2I Borisov, discovered in August 2019 by amateur astronomer Gennady Borisov. This latest detection immediately spurred a combination of excitement and debate within the global scientific community. When comparisons are drawn between these three interstellar visitors, some key distinctions emerge. ʻOumuamua, officially designated 1I 2017 U1, was the first of its kind ever observed, and it shocked astronomers with its highly elongated shape, unusual acceleration, and lack of a visible cometary tail. It was initially described as a cigar-like rock, though later studies suggested it may have been more disc-like, possibly resembling a fragment of a larger body. Its non-gravitational acceleration was attributed by some researchers to outgassing, but this remained controversial given the absence of a detectable coma. In contrast, 2I Borisov behaved much more like a conventional comet. It displayed a distinct tail, emitted gas and dust, and spectroscopic analysis revealed water vapor and carbon monoxide, aligning with expectations for a comet originating beyond the solar system. Its physical characteristics were therefore more familiar. 3I-Atlas has not neatly fit into either category. Observations have revealed a halo-like coma surrounding the object, but in an unusual orientation that challenges conventional cometary physics. When comets pass close to the Sun, sublimation of volatile ices releases gas and dust that forms a coma around the nucleus and drives a tail pointing away from the Sun due to solar wind and radiation pressure. With 3IATLAS, astronomers noted that the coma appeared to be positioned at the front of the object's trajectory rather than trailing behind it. This anomaly led to early speculation about whether the material being ejected was behaving differently from ordinary cometary dust, or whether the geometry of observation was giving a misleading impression. The glow of 3IATLAS has also been atypical. The brightness and intensity of the halo did not correspond neatly with models of sublimation expected for comets of similar size and solar distance. Normally, comets brighten as they approach the Sun, with their luminosity tied closely to the sublimation of water ice or other volatiles. In this case, the light curve of 3I Atlas suggested a more complex mechanism. Some researchers proposed that dust jets erupting from beneath the surface could explain the effect, while others pointed to the possibility of reflective materials that scattered sunlight in unexpected ways. Still, the glow remains unusual. Venus, Mars, and Jupiter. While planetary flybys by interstellar bodies are not inherently impossible, the proximity of these encounters has drawn attention. Jupiter, with its immense gravity, often plays a significant role in altering the paths of incoming comets, but for 3I-ATLAS, the sequence of near-planet approaches appeared remarkably coincidental. This raised questions about whether the trajectory could be purely natural or whether non-gravitational forces were at play. Astronomers have offered several possible interpretations for the anomalies. One possibility is that dust jets from beneath the surface of the nucleus are oriented in such a way that the coma is pushed forward relative to its motion, creating the illusion of a leading halo. Dust jets can act like tiny thrusters, subtly altering the movement of comets. Another explanation is solar heating effects. Depending on the rotation of the object, heat absorbed on its surface may sublimate volatiles in concentrated areas, causing directional outgassing that can affect both its brightness and trajectory. Observational factors must also be considered. The coma's apparent orientation could be influenced by the angle at which telescopes observe the object, as well as the scattering of light through its dust cloud. Efforts to resolve these mysteries are being supported by coordinated observations across multiple facilities. Ground-based telescopes, such as those at Mauna Kea in Hawaii, and the European Southern Observatory's Very Large Telescope in Chile, have been gathering high-resolution images, while space-based observatories like the Hubble Space Telescope and potentially the James Webb Space Telescope have been tasked with spectroscopic analysis. Spectroscopy is especially crucial, as it allows astronomers to determine the chemical composition of the coma and tail by identifying emission lines in the light spectrum. Then there's the question regarding the population of interstellar objects that pass through the solar system. Before 2017, no such bodies had been definitively observed, although it was expected that many should exist. With 3 detections in less than a decade, scientists are rethinking the frequency of such encounters. Studies based on the detection rates of ʻOumuamua, Borisov, and now Atlas suggest that trillions of interstellar objects may be traversing the Milky Way, with some entering our solar system every year. Improved survey systems, such as the forthcoming Vera C. Rubin Observatory in Chile, are expected to greatly increase the rate of detection. Each interstellar object carries with it invaluable scientific potential. They represent material from other star systems, possibly formed billions of years ago under very different conditions. Analyzing their composition can shed light on planetary formation, the distribution of volatiles in other stellar environments, and even the possibility of panspermia or the hypothesis that life's building blocks may be transferred between star systems via comets and asteroids. In the case of 3I-ATLAS, the combination of comet-like features and anomalous behavior makes it particularly interesting. As telescopes continue to monitor its progress through the solar system, the data gathered will contribute not only to understanding this particular visitor, but also to shaping broader insights into the nature and frequency of interstellar objects. But one man seems to have a very clear idea of the whole thing already: Harvard scientist Avi Loeb's hypothesis. Known for his willingness to challenge orthodoxy, Harvard astrophysicist Avi Loeb has consistently put forward high-profile hypotheses that straddle the line between bold scientific inquiry and controversy. His career spans decades as a professor of science at Harvard University and chair of its Department of Astronomy from 2011 to 2020. Beyond his academic credentials, Loeb has published hundreds of papers in peer-reviewed journals and authored several popular books, including 2021's Extraterrestrial, the first sign of intelligent life beyond Earth. Yet, What has set him apart from many of his peers is his repeated insistence that some of the most puzzling astronomical observations of the past decade could point to signs of extraterrestrial technology. His most famous claim came in late 2017, following the detection of one ʻOumuamua, the first confirmed interstellar object to pass through the solar system. Discovered on October 19, 2017, by the Pan-STARRS 1 telescope in Hawaii, ʻOumuamua defied easy categorization. Unlike comets, it displayed no visible tail or coma, yet it accelerated as though a force beyond solar gravity was acting on it. Many scientists suggested that the acceleration could be explained by outgassing, but no outgassed material was observed. Loeb published a paper in Astrophysical Journal Letters in 2018, in which he proposed that ʻOumuamua might be artificial in origin, perhaps a probe or a fragment of alien technology propelled by light sailing. His pursuit of evidence for interstellar technology did not stop with ʻOumuamua.
A cigar-shaped object named ʻOumuamua was the first known interstellar object from outside our solar system.
In 2019, the US Department of Defense released data confirming that a meteor had entered Earth's atmosphere on January 8, 2014, and disintegrated over the Pacific Ocean near Papua New Guinea. What made this object, later catalogued as CNEOS 2014-0108 and dubbed IM-1, remarkable was that its speed and trajectory suggested an interstellar origin.
With the spacecraft, you just reflect light off it and it's being pushed.
Loeb collaborated with Amir Siraj, then a Harvard undergraduate, to analyze the data and concluded that IM-1 was the first interstellar meteor ever detected. Building on this finding, Loeb led an expedition in June 2023 to the seafloor off Manus Island in Papua New Guinea. Using a magnetic sled, his team retrieved more than 700 tiny metallic spherules, each less than a millimeter in diameter, which he claimed had come from the disintegrated meteor. These spherules were subjected to analysis at Harvard's laboratories. Loeb reported that the composition of the particles was unusual, with elevated levels of elements such as beryllium, lanthanum, and uranium compared to typical terrestrial or meteoritic alloys. He suggested that the chemical profile did not match known natural samples, raising the possibility that the fragments represented materials engineered by an advanced civilization. When the third confirmed interstellar object, 3IATLAS, was discovered, Loeb once again entered the discussion with an interpretation that diverged from the mainstream. Initial observations of 3I, Atlas, revealed a peculiar feature. Instead of a comet-like tail trailing behind, the object appeared to exhibit a glowing halo at its front. For Loeb, this was not easily explained by conventional cometary activity. He proposed that the forward-facing glow might represent a light source generated internally, much like the exhaust of a power system. In interviews and essays published soon after the discovery, Loeb suggested that a compact nuclear reactor could be a plausible explanation, noting that human spacecraft have used onboard reactors for deep space missions. The trajectory of 3I Atlas further fueled Loeb's speculation. Its path brought it unusually close to Venus, Mars, and Jupiter, a sequence of planetary flybys that some astronomers considered a remarkable coincidence. While the consensus explanation was gravitational dynamics influenced by Jupiter's massive pull, Loeb suggested the possibility of controlled maneuvering. If 3I Atlas were a probe or relic of extraterrestrial engineering, the path could be interpreted as a deliberate course that optimized planetary encounters, much like how human spacecraft use gravity assists to conserve fuel. He emphasized that while the natural explanation remained far more likely, the pattern was nonetheless intriguing enough to merit investigation. Drawing on his earlier work with IM-1, Loeb raised the possibility that the emissions from 3I Atlas might include alloys or engineered materials not found in natural solar system objects. If the glow represented outgassing or particle emission, spectroscopic analysis could potentially reveal unusual chemical signatures. Loeb noted that in 2023, his team had argued that the spherules recovered from the Pacific showed evidence of exotic metallurgy. If an interstellar object could indeed carry such materials, then 3IATLAS might present a rare opportunity to study them in situ. His critics accused him of courting sensationalism, arguing that extraordinary claims without extraordinary evidence risk undermining public trust in science. Yet, his supporters countered that his work opened intellectual space for questions that might otherwise be dismissed too quickly. Loeb was performing a necessary role by challenging the scientific community and avoid prematurely closing off lines of inquiry. From Loeb's perspective, the implications of 3IATLAS, if spectroscopic analysis were to reveal emissions inconsistent with ordinary cometary volatiles, it would raise the prospect that humanity was observing technology from beyond Earth. Claims of alien technology have arisen many times before, from the Martian canals reported in the late 19th century to the WOW signal detected in 1977. Natural explanations eventually proved more convincing. Yet history also shows that progress often comes from those willing to push against consensus, whether in proposing that meteorites came from space, that bacteria caused disease, or that continents drifted. As 3I Atlas continues its journey through the solar system, astronomers around the world are gathering data with every available telescope, from the Very Large Telescope in Chile to the James Webb Space Telescope, positioned at L2. These instruments are capable of conducting the precise spectroscopic analyses that could confirm or refute Loeb's warnings about unusual emissions, whether they reveal exotic alloys or simply volatile ices behaving in unexpected ways. The study of 3I Atlas will for sure expand humanity's knowledge. The unknown alloys connection. When Avi Loeb led an expedition off Papua New Guinea to recover remnants of the 2014 IM-1 meteor in 2023, his team retrieved over 700 metallic spherules with unusual elemental ratios. Unearthly, one might say. Supporters pointed to the fact that interstellar objects are still poorly understood, with only 2 confirmed examples, ʻOumuamua in 2017 and Borisov in 2019, prior to 3I ATLAS. If IM-1 was truly of interstellar origin, then its spherules offered the first tangible samples from beyond the solar system, in Loeb's view. If the spherules retrieved in 2023 represented fragments of engineered alloys, then a larger interstellar body, such as 3IATLAS, might also be expected to emit substances with distinctive non-terrestrial signatures. The challenge lies in how such emissions could be detected. Astronomers rely heavily on spectroscopy, or the study of light across different wavelengths, to analyze the composition of distant objects. When sunlight reflects off or passes through the dust and gas around a comet-like body, the spectrum recorded by telescopes can reveal the presence of specific elements or molecules. Hydrogen, oxygen, carbon monoxide, and water vapor all produce characteristic spectral lines, which can be identified even from millions of kilometers away. If 3I Atlas were to emit material with exotic ratios of elements, those signatures might appear in spectroscopic data as unexpected or anomalous peaks. Already, observations from the James Webb Space Telescope have demonstrated that 3IATLAS has an exceptionally high carbon dioxide to water mixing ratio of approximately 8 plus or minus 1. This is one of the highest ever measured in a comet, and significantly above the expected trend at its distance from the Sun. This ratio has prompted discussion about whether the carbon dioxide might be serving as a propulsion-like mechanism or fuel analogous to outgassing in conventional comets. Moving forward, the confirmation of alloys unknown to Earth in an interstellar object would represent a paradigm shift in multiple scientific fields. For astrophysics, it would provide the first direct evidence that advanced technological artifacts exist beyond the solar system, proving that human beings are not the sole technological agents in the galaxy. For materials science, it would open a window into engineering techniques far beyond current human capabilities, potentially revealing novel ways of combining elements or producing stable compounds with unique properties. The mere identification of non-terrestrial alloys could stimulate entirely new lines of research, from replication attempts in laboratories to exploration of their industrial or energy applications. Loeb himself has acknowledged that the stakes demand a rigorous scientific process to avoid false claims. Extraordinary evidence is required to substantiate extraordinary hypotheses. The controversy surrounding his interpretation of the ʻOumuamua spherules illustrates the dangers of over-interpreting ambiguous data. While the unusual elemental ratios were intriguing, they did not conclusively prove artificial origins. Anomalies in three IATLAS's coma or trajectory might eventually be explained through natural cometary physics, such as irregular outgassing, solar heating effects, or observational artifacts. Prematurely declaring evidence of unknown alloys could risk undermining public trust in science if subsequent analyses demonstrate more mundane explanations. Astronomers have to now consider what signatures would definitively indicate alien engineering, and whether humanity has the observational tools to recognize them. Even if the object ultimately proves to be entirely natural, the exercise of considering extraordinary scenarios enriches the scientific process by clarifying methods, sharpening definitions, and preparing researchers for future discoveries. With survey systems such as the Vera C. Rubin Observatory expected to come online in the late 2020s, the detection of interstellar visitors may become far more frequent, providing more opportunities to apply these lessons. In the end, Loeb's interpretation of the ʻOumuamua spherules and his extrapolations to three IATLAS may remain controversial. Well, at least for now, but they highlight the stakes of studying interstellar objects, the potential to uncover evidence of technology not made on Earth. Humanity must now look more closely, analyze more rigorously, and remain open to the possibility that the universe contains wonders beyond current imagination. Whether natural or engineered, 3 IATLAS shows us how little we yet know about the materials and processes beyond our solar system. Its anomalies continue to spark debate, its emissions continue to be monitored, and its passage through our celestial neighborhood serves as both a scientific opportunity and a philosophical provocation. The true nature of its glow and composition may not be resolved for years, but in raising the possibility of alloys unknown to Earth, Avi Loeb has once again pushed the boundaries of inquiry. As humanity awaits further data, the central lesson is that every interstellar visitor deserves the closest scrutiny. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.